the neuromorphic or the semiconductor, right? Today I talked to another student, we were saying, oh, it was very amazing. Nowadays, even if we see COVID-19, the electronics is the one that is still growing, right? 20 years ago, the visiting scholar in my school told me that you should quit semiconductor. This is the end already. Okay. Is that okay? Any questions? Now I reviewed this for so long because now we are going to really explain to you why we can have different resistance when you have parallel and anti-parallel state. Okay, so now here I shows the magnetic tunneling junction. I have a free layer on top, reference layer on the bottom. They are in parallel state because the magnetization is pointing in the same direction. Magnetization is due to the electron that are not moving. It's just like the external magnetic field. So anyway, you think that I have magnetic field pointing to the left in the reference layer. I also have magnetic field pointing to the right in the reference layer. Now, for the electron that you want to go from top to bottom, what do you need to do? Since this is insulator, how can you have electron going through an insulator? What mechanism is that? How does the electron go from top to bottom if MgO is insulator?
Tunneling.
Tunneling. So tunneling is very important. Good, right? So let's see how we tunnel. The main point is that we assume when tunneling, electron spin doesn't change. So if it is pointing to the left, after it tunneling, it needs to keep at the left, unless you have some mechanism to flip it. This is just like conservation of spin, conservation of energy, conservation of momentum. This is something related to the conservation of the spin, right? The spin, you cannot change it easily unless you have some external magnetic torque. So if this is the case, basically it's saying that on the free layer, because it's pointing to the left, right? And in this diagram, basically it's saying that pointing up, you see that I have more electron that is, instead of pointing to the left, right? Let's call this pointing to the, this side is pointing to the top, right? You just think about rotate it 90 degrees. So I have more electron pointing up than electron pointing down. This is okay. But if I want to tunnel, and same for the reference layer, I have more electron pointing up and less pointing down. If I want to tunnel, because electron spin doesn't change when tunneling, then only this blue, the pointing down one, has to go to the pointing down location. You cannot go to here, because if you go to here, you are flipping the spin, but there's no external mechanism for you to flip, right? Conservation of spin. It's just like that. You cannot say I jump to that the next room, then I gain more energy. No, because you need to have some mechanism. So you go from here to here, you need to go from blue to blue and red to red. Okay, and this is my analogy. If you say, I want to go from here to here, you don't have a lot of electron at the source, right? So this path doesn't have a lot of current. However, for pointing up, I have a lot of electron. At the same time, when I jump to here, I have a lot of available state because this one is low, right? So this is, the blue is very small, but the red is very large. So as a result, I have large current. Is that okay?
Hello, Professor.
You have question or what?
Yeah, actually, I
Uh-huh.
am not able to understand the thing.
Which part you don't understand?
The
Starting from
blue
where?
part, the electrons, like due to band tunneling, it goes to uh, the other blue part, right? And the red
Okay. Yeah. Yeah.
goes.
So if you want to tunnel, you have to tunnel from blue part to blue part. This one makes sense or no?
Yes, Professor.
Yeah, because you need to conserve the spin. Okay, the spin cannot change, so you can only tunnel to here. This part is only for the spin that is pointing up. So I don't have a lot of electron, right? Because this one has higher energy. That's why I asked you here. This is less, this is more, right? So I only have some electron here. So, and then my destination also don't have a lot of available state. Okay, so I go back to my back analogy. My back analogy was that these are the boys. They want to go to the restroom. And this is the boys' restroom. Okay, and I don't have many boys. I also don't have many restrooms. So the number of boys that can go to the restroom is very few. Is this okay?
Yes.
So do you understand why I say I don't have a lot of restroom here? Because this is very high. The energy is much higher. They can only tunnel to the low energy lower than tunnel to the same energy, right? This is the density of state here.
So basically, they can tunnel to the same energy or energy less than the
Yes,
previous
yeah.
one.
But here, let's just assume the same energy, because if there's no other mechanism, it's okay.
Yes, Professor.
Now for the red one is the girl. I have many girls waiting to go to the restroom. But at the same time, I do have a lot of vacancy restroom here, right? So for this tunneling, do I get a lot of current? I do, right? Because I do have many ladies want to go to the restroom, and also I have a lot of vacancy. So that's why I have a lot of current. So overall, I have small resistance. Is that okay? Now, what if they are anti-parallel? So because they are anti-parallel, right? On the top, let's assume it's the same. This drawing is not that good, right? But they're just different. On the top, because the external magnetic field is pointing up, right? This is just like, here is B, they all pointing up. B, and here is B pointing down. Because of this, I have more electron pointing up in the free layer. Okay, but I have more electron pointing down in the reference layer. Is that okay? And again, we still only the blue can go to blue, red go to red. Now for blue, I have very few electron from the source. Means I don't have many boys want to go to restroom. Although I have a lot of restroom that they can go. But overall, I only have a small current. And same for the red. I have a lot of electron here, right? But I don't have a lot of available state because here the energy is higher. So I also only have very small current for this. So overall, it is still small. That's why I have a high resistance, right? I have very small plus very large, maybe 1 plus 100 give me 101. And here I have small plus small, maybe 10 plus 10 give me 20. So that's why in parallel state, I have higher current, lower resistance. Now, this one is something I see if you can understand, right? Any question on this? And this is the only thing I want to teach in this class regarding the reading.
So the colors, the higher up they are on that y-axis, the more energy is associated with that.
Yes, because
Okay.
the y-axis is the energy. So you can imagine why I don't have electron here, because the Fermi level is here. Here is the Fermi level, right? So for those above Fermi level, it is not occupied.
And so for instance, on the left, the two red portions, it's a very large current because there's more electrons that can reach higher potentials on the right side.
Not high potential is that, first of all, if I want to have current, I need to provide electron. Do I have electron? I do have a lot of electron at the Fermi level, right?
Yes.
Because the x-axis is the density of state. So if I have the curve go to here, then I have more electron, right? And then same, when you apply bias, this will go down a little bit because of the Fermi level. But then I also have a lot of vacancy states here that it can tunnel, right? So I get a lot of current.
So the vacancy states are on the x-axis. Is that what you're saying?
Vacant state, yeah, the counting is from the x, right? The counting here, this 9, if you project to here, this is x is the n number of state. So for example, here saying that when your energy is this, then I have so much density of state. So if you are here, right, very small. But if it is here, a lot. Right? This may be 1, this may be 10.
Okay.
I think it can still be confusing, even you say okay, right? And any other questions? So yeah, go ahead.
I wanted to know in the anti-parallel state.
Yeah.
So for the front layer, like the upper layer,
Yeah.
the magnetic direction, the red colored part, which is pointing upwards, okay? There are a lot of electrons. So,
Yeah.
but due to poor band matching and high resistance, they are not able to tunnel towards the reference layer. And that's
No,
the reason.
they are not able to tunnel and then cause this high resistance. But why they are not able to tunnel? Because just imagine I have a lot of electron here. I want to go to here. It cannot go if there's no vacancy. It's just that you are lining up outside the classroom. If the classroom is so small, only have a few chairs, even you have a lot of people lining up, how many people can go into the classroom? It's only limited by the number of chairs in the classroom. And this is the problem here, because the energy got lifted up. So at this level, I have less vacancy, right? That's why they cannot go.
Okay, and for the blue part, though there is a lot of vacancy, but there are no lot of electrons.
Very good, right? I have a very big room, a lot of chairs, but only a few people line up outside the door. So when I open the door, I only get a few people going into there. Even I have a lot of chairs. So it's still small current. And for this case, it's even worse. No people, only one people waiting outside the classroom, and inside the classroom, only one chair. So yeah, you can go in, but I only have a very small current. Is that okay?
So all the states are occupied on the left part of the graph, the blue on the left, and then they go to the unoccupied states on the right?
Yes. And this 9 is the ideal situation at 0 Kelvin for Fermi level. That's why everything below this 9 got filled. All this above are not filled. right? So for tunneling, for moving, you always, those near the Fermi level can move. So we only need to look at the near the Fermi level. This one is Y, so I have a lot of electron. This one is Y, so I have lots of vacancy state. But when this energy got lifted up, this is short, so very few source, but tunnel to a very large destination. A lot of electron here, but tunnel to a very small destination. Is there any more questions? Okay, let's say, assume you are okay, right? But I really hope that you can, why understand this? It means you also understand all this band structure we have talked about, right? Think about that. So why is so special? It's even almost not learning anything new if you think about that. The only new thing is that, hey, now all the electron has up and down. Not every electron is the same. Now I have two groups of people now, up and down. In the past, you just treat electron the same. But when we have this external magnetization or external magnetic field, you are going to have two groups of electrons. And they have different energy. And that is the magic, right? So nowadays, people talk about a lot about spintronic. This is only one part of that. Spintronic is, I think, is going to change the world also, right? Because they use the spin as a signal. No longer whether you have a charge, it's talking about spin, or not current, not voltage, right? And they have very small energy, and that saves a lot of power, okay? So then, of course, earlier we say that this one, right, give us our P, which is smaller. This one give us our AP, and then our tunneling magnetoresistance is our AP minus our P divided by our P, like what I put here, right? What we discussed last time. And they are not much, maybe 80% or 100%, right? But here you also tell you something deeper. Maybe you don't need to really understand. The tunnel magnetoresistance, this is just a resistance, but this is talking about the so-called polarization, what they call polarization, right? Based on that paper that I uploaded. But this polarization is not really to, it's not really not magnetization, right? It is related to the so-called tunneling probability. So this is a very difficult topic because you need all the electromagnetism, what you learn in E140, and more than that, because E140 is macroscopic, right? You need to learn all those microscopic things, right? So a lot of quantum mechanics. And do you know that Maxwell equation itself fulfills relativity, right? Because it's a description of light. It has to fulfill relativity. And this is relativity combined with quantum mechanics, right? Becomes quantum field theory. Yeah. So it's very difficult, actually, right? So we don't need to go to that deep, right? Because I also don't know well, right? But anyway, the point is that you see that the conductions is related to the, this is the tunneling probability from left, right, into the insulator. Okay. And then this is the probability from insulator to the right contact. Right. And this is related to the decay in the insulator, right? So here, just to tell you that the theory is more complicated, but basically it can decompose as how the electron will tunnel into the evanescence state in the insulator. It decay because insulator, it doesn't have a state for it. So it decay, the wave function keep decaying. And then that wave function will tunnel into the right electrode. All together will determine the so-called polarization. And then you will get this tunneling magnetoresistance. The first equation is just the definition. You measure it in the lab, you get resistance, you got it. This one is more from the theory. If you know the material property, you can derive TMR, okay? But no worry about this, right? I only want you to understand why they have different resistance. Any questions? Now this is red. Then how do I write it? How do I write a state, right? When writing, basically is saying that I want to change, for example, it was in anti-parallel. I change it to parallel. So we are just going to fill up the table. Okay, so it is saying this. Now I have this reference layer maybe pointing up, and then the free layer may be pointing up, right? This is free layer. This is reference layer. I want to change it to parallel. It means that same as the reference layer pointing down. How do I change it? Because this might mean this is 0, I want to write it as 1. So what do I do? That is what it does. We're going to inject electron from reference layer. How do you inject electron from reference layer? It means electron go from reference layer to the free layer. So what voltage should you apply to the reference layer, positive or negative? If I want the electron to go from reference layer to the free layer,
Is it positive?
if I put a positive here, what is the direction of the current? Going up or down if the reference layer is positive?
The electrons move up.
How about current?
Moves down.
So you think if I apply positive voltage here, the current moves down? Current move from where to where? Positive to negative or negative to positive terminal?
Conventional moves from positive to negative.
From positive to negative, right? So it should move up. Current move up. Yeah. So then electron is moving down, right? Because it's opposite. So if I want to inject electron from reference layer to free layer, should I apply negative or positive?
Negative.
Negative, right? So negative at reference layer, negative voltage. Or maybe let me just say V smaller than 0 at reference layer. When I inject electron from reference layer to the free layer like this, what type of electron I have more? Right? It has to be the electron that is in the direction of the reference layer, right? So electron mostly, because I don't have more electron that is not in that layer, right? Because this is reference layer, this is the magnetization. I have more electron of this, right? Or just think about the nature is I inject electron from reference layer. I have more electron that align with the direction with the reference layer. Make sense? So electron mostly align with reference layer magnetization, right? Because it has more, right? So it means that suddenly I flood a lot of electron that is in the directions of reference to the free layer. And then what happened? And then this layer, this electron, right? You can imagine, right? I don't know, maybe let's say last year I used this example. Country A has a certain accent in English, let's say, right? And then they go to country B. If you flood a lot of people from country A to country B, they are going to change the accents in country A, country B, right? Because everyone got affected by them. How you affect them? Through this LLG equation. And I told you Landau, right? We talked about the Landau equation for ferroelectric, for negative capacitance. This is where Landau appears again. It is on how this external electron going to change the magnetization of this free layer. It's going to exert a torque to it. So eventually it's going to flip the magnetization of the free layer so that eventually it is parallel to the reference layer. It's just like country A's essence. So many people from country A go to country B. Then country B, everyone split the same essence as country A. Is this okay? And then, of course, and then why? Firstly, why everyone from country A will split their essence? Because they are all pointing, most of them are pointing up due to this polyparamagnetism, right? We also have some splitting another essence going, but not enough, right? Most of them, they come here, right? And then I have so many electrons pointing in the same direction as the free layer magnetization. Then you interact with the shell electron, then you flip their magnetization through this top. We don't need to learn this. I just show here to let you know that we have this equation. This tells you how the magnetization change with time. Any question about this? If you understand this, then the next one may be easier.
Professor?
Mm-hmm.
Here we're trying to change the direction from anti-parallel to parallel, right?
Yeah, like here. It was anti-parallel. I want to change it to parallel.
So where does it change actually when the electrons move from reference layer to free layer?
So when the electron enter the free layer, all the electrons are pointing down. Okay, the magnetization are pointing down. Then this electron pointing down is going to affect the shell electron on the free layer so that eventually they will point down.
So basically when we apply negative voltage to reference layer, whichever electrons that are tunneling towards the free layer will start pointing downwards.
Whatever tunnel from reference layer to free layer will keep its direction. But because the reference layer has more electron that is pointing down, so more electrons are actually pointing down. So it flipped the top one to pointing down also.
Just because there are more electrons in reference layer which are pointing downwards.
Yes. Just because we have more electron that is pointing down in rest. Here is pointing up, but right, just be aligned with the direction magnetization of the reference layer. Because of this energy splitting, you see we have more. Both of them will get injected to the free layer, but this one has more. So it has a lot. So it has more effect.
Okay, Professor.
Okay. Now, this is how I change from parallel to anti-parallel. How do I change it from parallel to anti-parallel? Right? Now, I want to write it differently. How do I do that? This is very difficult to understand, actually, right? It spent me a long time to understand. Actually, I learned this when I was in Synopsis, and we have a software to simulate, right? And my manager and I both didn't understand at that time. So it was parallel. How do you make it to anti-parallel? What we are going to do is to inject electron, not from reference layer, right? You know that reference layer doesn't work, from free layer. Okay, how do I inject electron from free layer? I should apply voltage smaller than 0 at the free layer, right? So I change the polarity. So the electron inject from the free layer to the reference layer. So for electron inject from the free layer to reference layer, are they mostly aligned with the reference layer or anti-parallel with the reference layer? They were in the same direction. And now I inject electron from top to bottom. Are these electrons going into reference layer aligned with the reference layer or opposite to the reference layer?
Opposite to the reference line.
Do you have more electron? Let's look at this figure. Do we have more electron pointing down in the free layer or pointing up?
Pointing down.
Pointing down, right? You need to follow the magnetization, right? So do you have more electron injected into the reference layer or that is pointing down or pointing up? Right? You see that you have more electron pointing down here. In extreme case, maybe you only have electron pointing down. Then when you have inject electron into our reference layer, all your electrons are pointing down, right? Correct?
Do you inject electrons to the from the reference layer to the free layer?
No. Here we say the goal is to inject electron from free layer to reference layer. Because we apply negative voltage at the free layer. Right? I apply negative voltage on the top, so electron need to go from the top to bottom. Make sense?
Okay.
Right? So I have electron going from top to bottom, right? So electron mostly aligned with the reference layer can tunnel. And this is related to this one also. Do you remember? Because they're pointing in the same direction, all of the current are mostly in the aligned with the reference layer. Right? So it's just like country A, all the people speaking a certain accent go to country B. And those speaking opposite will what? Stay in country A because they did not tunnel into country B. So those left, right? I should remove this, are mostly what? Anti-parallel. To the reference layer, right? So I have electron pointing down, also pointing up, but most of the electron pointing down can tunnel to reference layer. I only have some that is left behind that is anti-parallel. And because I have so many anti-parallel, again, it exert the torque through this equation, and then you flip it to another direction. Is this okay? Now let me make an example. For example, I think this is better. Let's say country A has English spelling, right? Center is C-E-N-T-R-E. Country B is American spelling. Center is C-E-N-T-E-R, okay? Now let's say country A at the beginning is the same as country B. Most of them spell American center, C-E-N-T-E-R. If during this process, I send all the people who spell center as in the American way to country B, then only the people that is spelling British way, T-R-E, will stay in country B. Then isn't that they will gradually change the culture and also the textbook? Eventually, the country B will be a country which spell T-R-E instead of T-E-R. Okay. When I change from anti-parallel to parallel, it's opposite. Country B is American spelling. Country A is British spelling. At the beginning, this is British spelling, but I keep sending people from the country B, all spell TER into country A. I keep sending a lot. Then gradually they change the culture. Everyone will spell TER. That is the analogy. Is this okay? No question? Anyway, I spent a lot of time to explain, but I actually feel that last year I went through very fast. Maybe no one really understand, right? I hope that we spend more time. At least you know learn something from here. Okay. So we are done with the STT.